Alrighty, good morning, lads and ladies. Welcome back to Calc 1. Today we are going to be looking more carefully at U substitution. In fact, all this week we'll be working on U substitution because it really is just that important. I don't want to drown it out in any other stuff. And we are right on pace. Terribly worried about moving quickly. I think it is appropriate for us to take our time. Take our time here. So let me go ahead and get the document camera rolling. I will swap over. to QCam. Last week, we kind of introduced U sub and we solved a couple problems with it. I do have that video uploading right now. And it should be available to you soon. I posted the link, but you know, YouTube takes their time processing things. But definitely by the time class is over today, you'll have access to last Friday's video if you wanted to rewatch that introduction. This, of course, is MAC2311, section 002. It's a lecture. And today is the 5th, 6th. April. So we only have a couple weeks left in the term. And one of the kind of big topics at the end here is the substitution method. Which is section 5.2. So last time I was able to convince you by kind of looking at the area underneath the square root of x minus 1 from 1 to 2, and the area underneath the square root of x from 0 to 1, that those two definite integrals should be the same. And then we saw one problem where we kind of took the same idea and generalized, applied to the sine 2 theta integral from 0 to pi over 4. I haven't actually written down the rule yet, though, so I think that's something we should certainly do. And it turns out there's kind of two versions of this rule. Most people just write down the version of it that applies to definite integrals. And I want to use the same notation that your textbook uses, so let me pop that up here real quick. Yeah, this is for indefinite integrals. I guess we can write that one down. Base G for the inner, okay. And then where's the substitution rule for definite integrals? Did I not state it? That's actually the more important thing. Yeah, okay. And they use G there also. All right. So let me flip back over here. Because this is the one we've done, I'll do substitution for definite integrals first. Your homework is about half and half, definite and indefinite integrals. It says if, you know, U is equal to G of X, where G is differentiable, then the integral from A to B of f of G of X times G primed of X dx. And if you kind of cover up the integral stuff, this looks very chain rule-y, right? Well, like we said last week, substitution is the integral version of the chain rule. It's a backwards chain rule. So it tells you how to integrate something that came from the chain rule. And the trick is to think of that inner function G as the new variable. So this becomes the integral of f of, well, G of X was U, and G primed of X dx is by definition du. And the trick is you need to change the bounds. So we saw that last time also, right, where the integral from 1 to 2 of the square root of x minus 1 became the integral from 0 to 1. And the way you found those new bounds, you recall, is by plugging the old bounds into your substitution. So this would be from g of a up to g of b. All right, this is our substitution rule for definite integrals. It looks a little bit intimidating, but with enough practice, you'll get good at this. The trick is to look at your integrand. You want to recognize your function as an outer and an inner, and then you need the derivative of that inner function, or at least something close to it, floating around over here. Before we get into examples, I'll go ahead and write down the theorem for indefinite integrals. We haven't seen any examples with this yet. But it works how you would think it does. You just don't have to bother with changing the bounds, because there aren't any bounds for indefinite integrals. So again, if u is equal to g of x, where g is differentiable, then the indefinite integral of f of g of x times g primed of x dx can just be rewritten as the integral of f of u du. So these are the two theorems, or formulas, if you like. And I think if you understand the rule for definite integrals, the rule for indefinite integrals is kind of a trivial case, subcase of those. Which is why we started with the definite integrals one. It also makes it just a little bit easier to understand when you can think about these things in terms of areas, which is the case with definite integrals, but not the case with indefinite integrals. So I'd like to look at some examples. And I'll start with an example of a definite integral, since that's what we've seen in the past. Yeah, that's fine. All right. So for example, maybe I want to evaluate the integral from 0 to 0 to 1 of the square root of 2x plus 1. Change it just a little bit, dx. Remember, the fundamental theorem of calculus says we need to find an antiderivative for this guy and then plug in these bounds. But because we cannot distribute that square root, and I'm going to remind you of this again and again in hopes that I do not see anybody do this on the test. Right, the square root of 2x plus 1 is super duper not equal to the square root of 2x plus the square root of 1. This never works. We have a bit of a challenge on our hands. If I could do this, then I could just apply the power rule to each of these. This would be root 2 times root x. This would just be 1, and you could take the power rule antiderivative of each of those. But since this shit doesn't work, we need to find some other way to calculate our antiderivative here. And just like with the square root of x minus 1 that we saw on Friday of last week, the challenge or the goal is to kind of get rid of the shit inside here. If this was just the square root of x, then I would know what to do. If it was just the square root of u or z, then I would know what to do. If I just had the square root of a single thing in here, just one variable, nothing separated with addition or subtraction, then I know how to find an antiderivative for that. That would just be a power rule. So I'm going to make the substitution u equals the inside of the square root, because then this will just become the square root of u, which is something I know how to find an antiderivative of. The first thing you need to do after choosing your substitution is to calculate your differential. Remember how differentials work? You just take the derivative over here. So du, the differential of u, would be equal to the derivative of 2x plus 1 times dx. And the derivative of 2x plus 1 is just 2. So du is equal to 2 dx. I always like to put this stuff in a little box. Kind of tells my reader what I'm doing and compartmentalizes all the work. The other thing, remember, we need to do is change our bounds. All right, if you look back at this formula, the bounds here are a to b. The bounds here are g of a to g of b. So you have to change your bounds when you do a substitution in a definite integral, always. I don't care what they told you in high school. I don't care what your last Calc 1 professor said. You need to change the bounds when you make a substitution in a definite integral. Our old bounds, our old lower bound was 0, and that was a value for x. When x is equal to 0, my new variable u is equal to 2 times 0 plus 1. All right, so you just plug the old bound into your substitution. You take this old bound, this old lower bound, plug it into the substitution here, and that will give you your new lower bound. So when x is equal to 0, u is equal to 2 times 0 plus 1. That's 1. And when x is equal to my old upper bound, 1, let's see what u is equal to. If you plug 1 in for x here, then u would be equal to 2 times 1, which is 2 plus 1. So that's 3. When x is equal to 1, u is equal to 2 times 1 plus 1, which is 3. All right. So this is all the stuff I need to make my substitution go. I've got the choice of substitution and the associated differential. And I see that my old bounds, which were 0 to 1, lead to the new bounds, 1 to 3. So what this tells me is that the old integral 0 to 1, square root of 2x plus 1 dx, is equal to the integral from 1 to 3 of the square root. All right, so we're just going to start plugging pieces in here. 2x plus 1, that's u. So the square root of 2x plus 1 is the square root of u. But now we get to this piece here, the dx. Du is equal to 2 times dx. And I need a du at the end here because I've changed my variable to a u. But I can't just swap the dx for a du because they're not equal to each other. Du is 2 times dx. So you have to come back and solve this for dx. And what you get is that 1/2 du is equal to dx. So in place of this dx, I'm going to write 1/2 du. And it's important that you see this piece is giving us this piece. So I want to take a second here and just answer any questions. Where did anything go? Why did we do anything the way we did? Where did any pieces come from? I want to make sure that everybody is rock solid on this.
I'm confused at the 1/2 du.
So remember, my goal is to replace this dx by its equivalent expression in terms of the new variable u. So I need to know the relationship between du and dx. That's what we have right here. Are we comfy with where this line comes from?
Yes, I see it now.
We took the derivative, and then I just solve for dx. That'll tell me what to put in here. So if I solve this for dx, I can multiply both sides by 1/2, and I get 1/2 du is equal to dx. So this dx can be swapped out for 1/2 du. And the kind of moral of the story here is that before we can integrate everything, every single piece must be rewritten in terms of the new variable. So the old variable was x and the new variable is u. But before I can do anything with my integral, like if I just wrote this as the square root of u times dx, I couldn't do shit with that. Before we can do any sort of calculus or any even algebra operations inside this integral, we need to rewrite every single piece, meaning the bounds, the original integrand, and the differential stuff. Every single one of those pieces needs to be replaced by its new variable counterpart. So like integral 0 to 1 needs to be replaced by integral 1 to 3. Square root of 2x plus 1 needs to be replaced by the square root of u, and dx needs to be replaced by 1/2 du. I have to do all those things before I can do any sort of integration, any antiderivative stuff. So Fabrice seems to be the same sort of question that Mackenzie was asking. Where did the 1/2 du come from? And this is the part that kind of takes a second to get used to. As soon as you write down your substitution, so we chose to substitute for the thing under the square root because I know that that's what's making life hard. As soon as you write down your substitution, you need to take the differential. And remember that the differential of u equals f of x is du equals f prime of x times dx. So you just differentiate this. The derivative of 2x plus 1 is 2. So du is 2 dx. You may remember this from back in, was it section 3.9, where we did differentials and linear approximation. We calculate the du. Du is 2 dx, and then we solve that for dx. So if I solve this for dx, I get 1/2 du equals dx. So this dx piece right here has to get replaced by what it's equal to, and it's equal to 1/2 du. So that's where that came from. Okay, I'm going to go ahead and move on now. So my next step, since everything in here is being multiplied, right? This is the square root of u times 1/2 times du. That 1/2 is a constant multiple. It can come out front. Now I'm left with 1/2 integral 1 to 3 square root of u du. And we think of this like a new problem. If I was just handed this right out of the gate, I would know what to do. I rewrite the square root of u as u to the 1/2, and I apply my power rule. So that's what I'll do here. 1/2 integral 1 to 3 u to the 1/2 du. So still haven't found my antiderivative yet, but I'm rewriting this in a way that will make it easier for me to see how to find the antiderivative. Who can help me with the antiderivative step here now?
Is it like 2/3 u to 3/2?
Yeah, very good. So we follow our power rule because this is now a straight up power function. When we take our antiderivative, the integral symbol and the du go away, and they get replaced by these brackets. The power rule says if you just have some variable to a power, the way you find an antiderivative is you add 1 to that power and divide by the new power. So if I add 1 to 1/2, I get 3/2. And then I would divide by 3/2. And what Mackenzie's doing is something that you guys should get comfy with at some point. Dividing by a fraction is the same as multiplying by its reciprocal. It's always going to be the next step. So rather than writing divided by 3/2, I'll just write multiplied by 2/3. And then since this is a definite integral, I don't write a plus c, but I do write my evaluation brackets. Again, if you've learned this in high school, you may have been told that you need to go back and plug in this 2x plus 1. But for definite integrals, that's not true. And that's why we change the bounds. So you don't need to plug anything back in here. You just evaluate between these two numbers. We don't need to go back to x's. We have these new bounds. We have this kind of wholly fresh problem, totally its own thing that we can just solve. So I'll plug in 3 and subtract what I get when I plug in 1. That'll give me, 2/3 times 3 to the 3/2 minus 2/3 times 1 to the 3/2. Now 3 to the 3/2 is not a nice number. It's the square root of 3 all cubed. Or if you like, it's the square root of 27. But not a nice number. This, however, is a nice number. This is the square root of 1 cubed. So the square root of 1 is 1, 1 cubed is 1. So this whole piece right here is 2/3 times 1. So you get 1/2 times 2/3, 3 to the 3/2 minus 2/3. And you can factor the 2/3 out if you want. When you factor out this 2/3, you'll have 3 to the 3/2 left in the first piece. And when you factor a 2/3 from this, it'll just become minus 1. The 2's cancel here. And you get 1/3 times 3 raised to the 3/2 minus 1. And that's plenty nice. You don't need to do any more than that. You may notice that this 2/3 could have been factored out right away. And this is one of those neat facts that the evaluation bracket is also a linear operator of its argument. Yeah, if you stopped here, this would be fine as well. On a test, I would want you to get at least this far. You can stop here on an exam. I would want to see that you know that 1 to the 3/2 is 1. And if this could be simplified, I would want to see that simplified also. So this line would be the appropriate place to stop on the test if you're trying to conserve time. Okay. Other questions on this guy? Something you'll notice is that these problems are going to get longer, right? The problems in general related to integration tend to be longer problems than differentiation problems. Don't be surprised if some of these take you a few pages. Certainly, it's not uncommon to have several pieces of paper burned on a single problem here. Let's find ourselves another example. We can talk through each one a little bit more, yeah, if we want. So here's my original integral. I chose to substitute for the thing under the radical because I recognize that it's sort of the algebra of the radical that's making life hard. I don't know how to find an antiderivative for this whole thing right away. None of my rules apply. right? I have a power rule that would work if this was just like x to the 1/2 or the square root of x. I have all sorts of other rules that tell me I can split things up over addition and subtraction, pop out constant multiples. But since you cannot distribute that square root, there is no way to split this up, right? That square root kind of puts everything in one little package and says, fuck you, you can't open me. So rather than trying to open the package, which would not be allowed, we relabel the inside of the package as a single quantity. We choose to make the substitution u equals 2x plus 1 because it gets rid of the addition or subtraction under the square root. If this was just the square root of u, then I'm happy. So we've chosen that substitution. My next step is to calculate the differential. Now remember, if u is equal to g of x, then the differential du is defined to be g primed of x times dx. So here, if u is equal to 2x plus 1, then du is equal to the derivative of 2x plus 1, which is 2 times dx. Having calculated this, we now change our bounds because it's a definite integral, it has bounds, but these old bounds are x values. Remember, the thing we're finding here is the area underneath the square root of 2x plus 1 from x equals 0 to x equals 1. Since I'm changing my variable, I need to change my bounds. These are old x values, so I need to cook up some new u values, new bounds that are appropriate for this new variable. To do that, I plug the old bounds into the substitution. So my old lower bound was x equals 0. To find my new lower bound, I take x equals 0 and I plug it in here. So if I plug 0 in for x here, I find that u is equal to 2 times 0 plus 1. 2 times 0 plus 1 is 1. So when x is equal to 0, u is equal to 1. I do the same thing with the upper bound. When x is equal to 1, what is u? Well, I plug it in here. If I plug a 1 in here, I get u equals 2 times 1 plus 1, which is 3. So my old upper bound was 1, and my new upper bound is 3. So these guys tell me the new limits of integration. They tell me the things that are going to be replacing the 0 and 1 here. The old integral from 0 to 1 becomes the new integral from 1 to 3. The square root of 2x plus 1 becomes the square root of u, because u is 2x plus 1. We got to choose that. The only tricky piece is to figure out what the fuck do I do with this dx? All right, remember dx, you can think of this as the infinitely small width of the infinitely many rectangles that make up the little area. What this substitution does, if you want to think about it that way as a coordinate transform, is it stretches things out. It stretches out the x-axis. In order to compensate for that stretching, we need to have narrower rectangles. The mechanics of it are very simple, though. You just come back to your du, and you solve this du equals blah, blah, blah dx relationship for dx. So I solve this for dx. That's going to tell me what I plug in here, right? This is dx. So whatever I'm going to plug in needs to be equal to dx. If I solve du equals 2 dx for dx, I get 1/2 du equals dx. So this dx piece becomes 1/2 du. Having plugged all those things in, I look at this guy as though it's its own problem, as though this is what I had in the book, or as though this is what WebAssign said to do. If WebAssign or my book gave me this, I would say, oh, look at that 1/2, that's a constant, he can come out. Okay, what's left is the square root of u du. So I need to rewrite that as a power, u to the 1/2, and then apply my power rule. And now, since it's a definite integral, after I apply my power rule to find an antiderivative, I need to evaluate between these bounds, the limits of integration. And that was what we did for the rest of the problem. We just plugged in 3, and then we subtract what we get when we plug in 1. and try to simplify. Well, so Fabrice asks a good question here. Every time I don't know the antiderivative of something, I can just substitute it. What you want to do, and this is sort of the meta thing here today, is learning how to pick your substitution. The first few homework problems I'm giving you guys tell you what to substitute for, but only the first few. And after that, you're on your own. The big game is that this, remember, is a backwards chain rule. So there's an inner and an outer, right? Just like when you differentiate using the chain rule, you've got an inner function and an outer function. You're going to substitute for the inner function. That's what you're going to do. You're going to substitute for the inner function. And then you hope that this derivative piece is floating around somewhere in your integral. So picking the substitution, Fabrice, is the challenging thing. If you can't use any of your other methods, at least for now, right? If it doesn't show up from your table, or you can't split up your integral into stuff that shows up from your table, yeah, the only thing we have is substitution. But down the road, there will be many other ways to integrate. In Calc 2, I'll teach you guys lots and lots of different tricks. But for now, if you don't see a way to get the antiderivative by just doing algebra and splitting it up, yeah, you're going to try to substitute. But picking the piece for which you substitute, like choosing U, is going to be the creatively challenging step here. Joe asks where the 2/3 came from. Remember how your power rule works, right? To find an antiderivative for U to the 1/2, if I want to anti-derive this, I need to add 1 to that power and then divide by that new power. So if little f of U is U to the 1/2, then big F of U, an antiderivative, would be U to the 1/2 plus 1 divided by 1/2 plus 1. That's the power rule, right? You add 1 to the power and then divide by that new power. That is U to the 1/2 plus 1. 1/2 plus 1 is 3/2. So that's U to the 3/2 divided by 3/2. And then dividing by 3/2 is the same as multiplying by 2/3. So if there's one thing I think that gets us in trouble in this class, it's algebra. Being comfy and confident with algebra is a big deal. So the 2/3 here is coming from dividing by the power 3/2. So this is all the good stuff here for this problem. I think it would be wise for us to look at one more definite integral, and then I'll show you some indefinite integrals. I don't want to undersell anything. This would be a better example to look at next, I think. Yeah, integral 1 to e ln x divided by x. Oh, you know what? Let's do the easier one first. We'll do a kind of warm up and then we'll come to this. This one is actually a much better problem than this, but just to make sure we're all on the same page, I'm going to run through this one. I'm going to run through it somewhat quickly. So integral 1 to 2 dx over 3 minus 5x quantity squared. So 1 to 2. Yeah. And this here is a 5. Okay. I would like to hear what you guys think. First, maybe a word on notation. Putting the dx upstairs like that is pretty common if the fraction has a numerator of 1, but to make this look a little bit more like what you're used to seeing, you could rewrite it like this. You can have the dx off to the side like that. All right, remember the dx is multiplying the integrand. So if you multiply a fraction with 1 upstairs, that would just put this guy upstairs. But here we go. So this is what I'd like to do. I need to find an antiderivative for this piece. But I have the same sort of challenge as I did in the previous one. This is like 3 minus 5x all to the negative 2.
So u would be 3 minus 5x.
Indeed. Before I write that, let me go ahead and rewrite it as I said it there, as 3 minus 5x to the negative 2 dx. And sorry, I don't have my panel up. I couldn't see. Was that Trevor? What was just said is exactly correct. I can't really distribute this power, right? Powers don't distribute over addition or subtraction. We could FOIL this out downstairs as 9 minus whatever 30x plus 25x squared. But then it's still downstairs. We still have the 1 over, and there's no nice way to clean that up. There's no nice way to split that up into individual pieces to which we could apply the power rule. So the move is going to be to substitute for this piece, substitute for the inside. So I'll substitute u equals 3 minus 5x. It's the third military flyover I did this morning. There are some loud planes going overhead. That means du is going to be what? What is the differential of u equals 3 minus 5x?
Negative 5 dx.
Very good, right? This piece would differentiate to 0. This piece differentiates to negative 5. And we always have to have our dx at the end. So this is negative 5 dx. Very good. All right. And then the other thing we do here, because this is a definite integral, we change our bounds. Our old bounds were 1 and 2. So when x is equal to 1, what is u equal to?
Negative 2.
Good. All right, if I plug 1 in for x here, then u becomes 3 minus 5 times 1, which is 3 minus 5, which is negative 2. And when x is equal to 2, what do we get?
Negative 7.
Very good, right? We'll have 3 minus 5 times 2. 5 times 2 is 10, so that's 3 minus 10, which is negative 7. This does something kind of nifty. These are called orientation reversing substitutions. I'll show you what I mean. Let's go ahead and start plugging things in. Integral 1 to 2 becomes integral negative 2 to negative 7. And you're used to the top guy being bigger, right? But negative 7 sits to the left of negative 2 on the number line. This is kind of backwards. So that's what I mean by orientation reversing. Not important for you to know the name or anything, but it's just a nifty fact. 3 minus 5x all to the negative second power is now going to just be u to the negative second power. Because 3 minus 5x is u. What about dx? What is he going to become?
Du over negative 5.
Yeah, all right, we come back here, we solve this for dx, and I would write it as negative 1/5 du equals dx. You could write it as du over negative 5 if you wanted to, but at some point we're going to have to pop a 1/5 out. So I think it's worthwhile to write it like that at first, but both are correct. So this becomes u to the negative 2 And then remember, this is multiplication, right? The differential is multiplying the integrand. So we want to write this negative 1/5 in parentheses. Otherwise, it's going to look like it's being subtracted. Like that. Now, I've made a few comments on tests and study guides and things to that effect in the past, and I'll ask that you take it to heart. Without these parens, it's very easy to misinterpret that as u to the -2 minus 1/5, which is not the same as u to the -2 times negative 1/5. So when you're multiplying things, especially things that are negative, please put them in parens. Just like in the last problem, I can shuffle this constant multiple out to the front. And I get negative 1/5 integral -2 to -7. And then this is u to the -2. I can ditch these parens now, right? Because this is a single piece. And now I go from something where I don't know the antiderivative to I do know the antiderivative, right? And the trick again was just to substitute for the inner function. Kind of if you had to differentiate this, your outer would be the power and your inner would be 3 minus 5x. Since this is a backwards chain rule, the game is to substitute for the inner. One little comment. Before I take the antiderivative and plug in bounds, remember we said this is orientation reversing because like -7 is not bigger than -2. It's to the left of -2 on the number line. -2 is bigger than -7. If I want to, I can take this negative right here, suck it into the integral by flipping the bounds over. I can rewrite this as positive 1/5 integral from -7 to -2, u to the -2 du. The rule here is that integral a to b, let's say f of x dx is equal to negative integral b to a f of x dx. We can flip the bounds over, and you can think of it as sucking up or spitting out a negative. So because I like to see the larger number on the top and the smaller number on the bottom, this is kind of unsettling. -7 is more negative than -2, so he really belongs on the bottom. And if I want to, I can soak up this negative by flipping these bounds over, just like this rule says. Now I can calculate an antiderivative, and we could have done it from this step. It wouldn't hurt you to not flip the bounds. I think it's just nicer. You'll have more negatives to play with at the end if you don't, but you could have left it as it is. The antiderivative here, again, follows from the power rule. If you add 1 to -2, it becomes -1. So this is u to the -1. And if you divide by -1, that's the same as multiplying by -1. All right, so this is -1 times u to the -1. And if I'm being careful, I should write it like this. And this gets evaluated between these bounds. Like so. Questions up to here? Okay, I can do a handful of things here. This -1 can pop out, making the 1/5 outside negative once again. And then u to the -1, that's just 1 over u. So it might make life a little bit easier if we rewrite it this way before we plug in the bounds. And I'll get my -1/5 times 1 over -2 minus 1 over -7. And again, just to be clear what's being subtracted and what isn't, we'll write it like this. I'll continue simplifying up here. This is -1/5 times 1 over -2 is -1/2. And then I have minus -1/7. That's going to become plus 1/7. And then my common denominator here should be 14. This is -7/14. This is +2/14. And -7 plus 2 is -5. So this is -1/5 times -5/14. And the 5's cancel. The negatives eat each other up. And we get +1/14. Gucci, any questions on this? Okay, I think I mentioned last week that kind of your skill with USub is one of the best predictors of success in Calc 2. So again, practicing this is so important. Your homework set this week is somewhat long, and it's all U substitution. This is what we're going to be doing all week. So the problems are going to get progressively harder and harder as we go. I'm going to do one more definite integral, and then we're going to switch to indefinite integrals. Before I move to this last definite integral example for today, I want to show you something that I added to your modules last week. So if you come into the modules, in case you've forgotten, there's lots of shit here to help you out. Lots of links to websites, videos, all sorts of things. You want to know, how do I graph a rational function? How do I graph piecewise functions? How do I get good at solving inequalities? I forget how to use the chain rule. Oh, here's some examples. I forget, what the graphs of f and f prime look like. There's examples. If you come down to the bottom, under integration resources, I've added our first example here. Our first little page. And it's about why we have to change bounds when we substitute indefinite integrals. This is something that, oh, no, that's not the right link at all. I don't know why I have a Zoom link there. That must have been an error. I'll fix this. This is, I have it in my Calc 2 class, a really nice page explaining why it's necessary to change bounds. But it goes deeper than that because there's more going on in substitution than just the change of bounds, right? And this is actually a very similar example to the one we looked at the other day where you're comparing the area, like under the red curve here, from 0 to 1/2 to the area under the blue curve from 1 to 1.5. And you see those areas are the same. That's why you got to change the bounds. We talked about it. But there's something else going on here, and it's understanding what's going on with the dx. I think this is the piece that people have the hardest time understanding. And we've talked about it in terms of widths of little rectangles. And that works great as long as dx is a constant, which for all of our examples so far, like here, dx was -5, or sorry, du was -5 dx. As long as your differential is equal to a constant times the other differential, then you really can just think about it in terms of widths of little rectangles. But what if that's not the case? What if when you take your differential, you don't get a constant? It turns out that some substitutions shrink the little rectangles more in one place than in the other. it might shrink the little rectangle's width over here, but then stretch the little rectangle's width over here. What you're doing is called a coordinate transform, and it's actually a beautiful and deep thing that you'll study more intensely in Calc 3. But the upshot is you can still think of it as stretching and shrinking parts of the horizontal axis. It's just that if your differential isn't constant, it will stretch and shrink different parts of the horizontal axis by different amounts. And this picture is so far the only place on the internet I found a decent representation of this. So I invite you to read this link. I'll fix it in the modules right now. And then think about that as we're working this next example. All right, that's fixed. So the next example is the one from the book that we had right here, integral 1 to e ln x over x dx. So this will be our first example of a substitution problem where the differential isn't constant. And it's also kind of the first example of a substitution problem where choosing the thing to substitute for isn't entirely obvious. If I tried to find an inner and an outer function here, I would be hard pressed to do so. It kind of looks like the only inner function is x. But substituting u equals x doesn't change anything. It never does anything. It's never worthwhile. All it does is relabel the integral. So I think it would be helpful here to rewrite the integral like this. Remember, we are really looking for an inner and an outer, but we need the derivative of the inner function to show up also. This is what you see in the formula here, right? You've got your outer and your inner, but then you've got the derivative of the inner here. So when you're choosing what to substitute for, if your inner function has a constant derivative, you can basically ignore this, right? It'll just pop out as a constant. But if the derivative of your inner function is not constant, you need it or a constant multiple of it hanging out next to dx. So having looked at that and rewritten this, what do you think would be good to substitute for so that I can think of this as my du? Who would have derivative or differential 1 over x or 1 over x dx? Another way to think of this, what piece here is hard to find an antiderivative for? I know how to find an antiderivative for 1 over x, but do I know an antiderivative for the natural log of x?
We do.
Or
sorry, I mean for the derivative of ln, my bad.
Yeah, so the derivative of ln x is 1 over x, but an antiderivative for ln x, I actually don't know. It requires a method called integration by parts. And I will teach it to you in the second week of Calc 2. So this piece on its own is hard to antiderive, and its regular derivative is this. So if I make the substitution u equals ln of x, then du will be 1 over x dx. And compare that to what we're looking at here. Do you see how this will be nice? This whole piece, ln of x, would become u. And this whole piece, 1 over x dx, is exactly du. It's very slick. And this sort of thing is what most substitution problems look like. We also need to worry about the bounds. So when x is equal to 1, what is u equal to? Remember how we do this? We take this old lower bound and we plug it in for x here. So when x is equal to 1, u would be equal to the ln of 1. Yeah, Trent's got it in chat. The ln of 1 is 0. So when x is equal to 1, I'll even write it like this. U is equal to the ln of 1, which is 0. So this is just one of the many reasons why you need to know these function values. All right, and you'll see this show up with trig stuff. You'll see this show up with exponentials. You'll see this show up with logs. Knowing these are critical. Similarly, when x is equal to e, u would be the natural log of e. And somebody else help me out here. What is the natural log of e?
1.
Yeah, very good, 1. All right. So my new integral is going to run from 0 to 1. So I'll say, okay, integral 1 to e ln of x times 1 over x dx, just rewriting the problem, is equal to integral 0 to 1. The ln of x is just u. And look at this shit. 1 over x dx is exactly du. Now, there's a handful of ways you could think about it. You could still solve this for dx and say, okay, dx is equal to x du. So the 1 over x and the x from the differential cancel. Or if you're clever, you just observe that these are the same, right? That these match up perfectly. So you get just the integral of u du. I'll show you how to think about it the other way also, right? Plugging in and canceling. But this is really the kind of higher brow way to do this. So 1 over x dx is du. Right? Because when we calculated du, that's what we got. It was 1 over x dx. We just got fucking lucky here, basically. That my du, as calculated from this substitution, is precisely the thing that was hanging out here. That's very nice. It won't always happen that way. But for a first example with a non-constant differential, it's very nice that we see, oh, 1 over x dx. Oh, 1 over x dx. That's exactly du. Lucky us. And now this integral 0 to 1 of u du, that's like, we've been doing that for weeks. That's not hard at all. An antiderivative for u is 1/2 u squared. And I evaluate this from 0 to 1. So that's 1/2 times 1 squared minus 1/2 times 0 squared, which is just 1/2. Easy peasy, lemon squeezy. I said this would be my last example of definite integrals, but I think it's wise to do one more where we get to play around with the differential like this. Oh, no, I guess we can do it in the context of an indefinite integral also. Well, maybe it's worth doing one more. How are we doing on time? 10:30. We got all the time in the world. Okay. metric function. Second. Let's do, maybe we'll switch to the indefinite intervals. We can do that. Sure, why not? Okay. Indefinite integrals are easier. Same thing, you just don't change the bounds. So if I wanted to evaluate, say, the integral of x times the cosine of x squared dx, this is an indefinite integral. But it's also a substitution problem. Remember, we have a sort of separate formula for substitution in indefinite integrals. It looks the same, it just doesn't have any bounds. When I look at this guy, specifically when I look at the integrand here, my focus is drawn to the cosine, right? This x, I'm not going to pay attention to him right now. I look at this piece and I notice that it has an outer and an inner. And also, the derivative of this inner is a constant multiple of the x over here. If I wanted to, I could rewrite this. It's not necessary, but I could rewrite this as cos of x squared times x dx. And that's thinking about the recipe from substitution, right? That's thinking about how to make this look a little bit more like this. So then the move here is to substitute for the inner function, right? Same as all these other guys, substitute for the inner. Substitute u equals x squared. Because then du is going to be 2x dx. And normally over here I would have bounds, but I don't have to do anything. There are no bounds. It's an indefinite integral. So that's all. If I start trying to plug these things in, I see right here I have a cosine of x squared. That's going to be the cosine of u. But then I have this x dx term over here. I could multiply both sides of this by 1/2 and say, okay, that means 1/2 du is equal to x dx. And then I would replace this by 1/2 du. But I wanted to show you the other way of thinking about it, because that's kind of very similar to what we did up here. So I said, one way you can attack this is to just always solve for dx. So let's do that. If I solve this for dx, then I get 1 over 2x du is equal to dx. Everybody comfy with that? So this here I had cos of x squared, and then I have this x. And now dx, I can replace by 1 over 2x du. And notice that the x's cancel. So what is left there is going to be the 1/2 du that I would have had if I'd done it the other way. Remember what we said earlier, that it's crucial that you get rid of all the old variable stuff before you integrate. So if these x's hadn't canceled perfectly, I would be in some trouble. And that turns out to be kind of the meta challenge, or the larger challenge here, is picking your substitution such that two things happen. First, your integrand becomes something you know how to antiderive, right? That you simplify the integrand by your substitution. The other thing that you need to make sure you do is choose your substitution so that the differentials all cancel out very nicely. In other words, so that all the x's go away. And that did happen here. So what we'll get is the 1/2 popping out, integral of cosine u du. And we know an antiderivative for the cosine of u, right? Remember, indefinite integrals are different from definite integrals. Definite integrals always come out to a number. Indefinite integrals like these always give me an infinite family of functions, all the antiderivatives. So I'm just trying to find the antiderivative for cos u here. That's all this is asking. Who differentiates to cos u? What is an antiderivative for cos u?
Sine.
Sine
Sine of what?
u.
Good, 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 good. So I get 1/2 sine of u. And since this is an indefinite integral, I slap on my plus c. Remember, infinite family of functions. That's one last thing to do. Again, this is a difference between definite integrals and indefinite integrals. If I handed you this problem and you gave me this answer without any of the steps in between, my big question would be, what the hell is u? You know, I asked you about apples. I asked you about x's. That's for an antiderivative of x cos x squared. And you tell me it's 1/2 sine u plus c. I'm like, well, that's nice, but I don't understand how these are related to each other. They don't even have the same variable. With an indefinite integral, you don't need to change bounds, but at the end, you do need to plug this back in. So this 1/2 sine u plus c, we need to plug back in u equals x squared. And we get 1/2 sine of x squared plus c. So when you're doing an indefinite integral by substitution, you have to plug back in the variables. You have to go back to the original variable at the end. And sometimes you'll do 2 or 3 substitutions, and you'll need to chase all the way back up through those. With definite integrals, we don't need to do that. We can change the bounds, and it's like a totally fresh problem. But here, the thing we get after doing the substitution is not a totally fresh problem. This variable u is related to the original variable x through a concrete relationship, and since I'm looking for the most general antiderivative of this function, my answer needs to be expressed in the terms of the same variable, the original variable. So with indefinite integrals, when solving indefinite integrals, via substitution, we need to plug in the old variable. But, and this is important, at the end. All right, we wait until the very end to do this. You can't plug back in the old variable before you integrate. That would never work, because then you'd have like cos of x squared du, which doesn't make sense. So after you take your antiderivative at the very end, that's when you plug back in the old variable. Questions on this? All right, I'll give you a minute to write. I'm going to refresh my coffee and then we'll look at one or two more examples.
It's the antiderivative.
Yes. Oh, Joe, yeah. Yeah, so we were taking an antiderivative, right? Once we got to this step here, the antiderivative of cos u is sine u. Remember, when you take your antiderivative, the integral symbol goes away. That's sort of the idea. Okay, let's try a couple more examples. What's fun? That's fun, that's fun. All right, I got two in mind. This next one is a favorite. And you'll see a version of it in your homework. Here I want to evaluate the indefinite integral of e to the x over 1 plus e to the 2x. And at a glance, it's not obvious what's the inner function, what's the outer function. But definitely it's those e's that are making things weird. An algebra rule that will help us that if you have a power raised to another power, that's the same thing as that first base raised to the product of the two powers. So I'm thinking about the blue while I look at e to the 2x. This tells me that e to the 2x is the same as e to the x all raised to the 2. And this is an important trick. We're going to see variations on this algebra trick all the time. Are we all comfy with why e to the 2x is the same as e to the x to the 2? You could also think of this as e to the x times e to the x, which would be e to the x plus x, and x plus x is 2x. That's e to the 2x. So here I would rewrite this as integral e to the x over 1 plus e to the x squared dx. And now maybe I can see an inner function. Does anybody see the inner function here?
E to the x.
Yeah, e to the x. So let's go ahead and try that substitution. If u is equal to e to the x, then what is du?
E to the x.
E to the x dx, yeah. And again, we're looking at an indefinite integral, so I'm not worried about bounds. I can solve this for dx. And that would give me 1 over e to the x du is equal to dx. So what do I have? I have downstairs here, certainly 1 plus u squared. And what I see is that my differential term has an e to the x in it. So this e to the x upstairs, I don't want to replace that by u, even though I could. I realize it's going to cancel with the e to the x from my differential. So what I'll do here is I'll write this as e to the x, and then dx is 1 over e to the x times du. And we need to kind of have this foresight. I know that my differential has an e to the x in it, so I will need to let that interact with one of the e to the x's from the original. Now downstairs here, this guy is not going to be able to interact, for one, because he's downstairs. For another fact, he's raised to the power of 2. But this guy upstairs here, he can. In fact, he cancels perfectly. So this becomes integral 1 over 1 plus u squared du. And we know an antiderivative for 1 over 1 plus u squared. If you're having a hard time figuring out what's up with this the differential here, I'll show you, I'll run through this a second time doing it the other way. But what is an antiderivative for 1 over 1 plus u squared?
Tangent u?
Almost.
Arctan?
Yeah, arctan, or the inverse tangent of u. So remember, the derivative of regular tangent is secant squared, but the derivative of the inverse tangent, or arctangent, is 1 over 1 plus u squared. So here we have arctan, or inverse tangent of u. And then because it is an indefinite integral, again, we'll plug back in. So this is the inverse tangent of e to the x plus c. And I said it just to make it clear, this particular trick, integrals like this, a little u sub into an arctan thing, these are favorites of mine. They're really nice problems, and it's not unlikely that you'll see something like this on exam 3 or on the final. Before I move away from this one, I'll go ahead and let this be our last example because we're a little short on time. I want to address the other way of thinking about the differential. Right, so I know most people, when they first learn this especially, they like to think of it as solve for dx and then plug in and cancel. That's fine. But there was that other way of thinking about it that I showed you when we did the ln of x over x integral, and that other way of thinking about things, I think, is clearer here. So the alternate way of thinking about the differential here is to take my integral e to the x over 1 plus e to the x all squared dx. We still do that algebra trick. And then I rewrite this in the way that looks more like the substitution formula, the theorem. By taking this e to the x and putting it over here. So when I look at this and realize I want to substitute u equals e to the x, I know that the derivative of e to the x is e to the x. So the differential du is going to have an e to the x in it. So I should try to group the derivative of my inside over here with the differential. Right, if you look at that theorem one more time. The derivative of my inner function is always set aside over here with the differential. So if I know that my inner function, the thing that I'm going to substitute for, is e to the x, I should try to, if I have a copy of e to the x to play with, put it over with the differential so that it looks like, you know, outer of inner, which is like 1 over 1 plus u squared with u equal to e to the x, times the derivative of the inner. The derivative of e to the x is e to the x. So if I rewrite it this way before I substitute, I think the substitution looks a little more clean. And there's less chance of getting confused about what to do with the extra e to the x. Because, just like with the natural log integral we did earlier, this piece, e to the x dx, is exactly equal to du. So if you can think ahead a little bit and put the derivative of your inner function next to the differential, if it is already there, if the derivative of your inner function, here my inner function is e to the x, its derivative is e to the x, here's that. If you have a copy of g primed to set over here next to dx, like we've done here, it can make it easier to see what to do with the differential. So here du is e to the x dx. Oh, well, here's e to the x dx. So this must be du. And then everything else is my function. So it gets us to the same place, just a little bit faster. This is 1 over 1 plus u squared du. Same thing that we got before. Of course, that's arctangent. And then again, you would plug back in. All right. But this way of thinking about or working with the differential is slightly more grown up, maybe. It definitely looks more like the theorem. And I think there's less room for confusion because you might be tempted to replace this by u, when in fact you really shouldn't, because it gets gobbled up by the differential. It gets eaten up by du. Du's got an e to the x dx in it. So this du is going to gobble up this e to the x in addition to this dx. And I think it's a little bit easier to see when you think about it like this. But that is it for me for today. You do have a new homework set up. It is all u sub. That's all we're doing this week. So on Wednesday and Friday, we will practice a little bit more. These problems have, you know, difficulty levels that are all over the place. Some of them are very, very easy. Some u subs are very, very hard. Unfortunately, Fabrice, I really don't have time to talk right now. I got to move to another class, but if you can come by my office hour this afternoon, we can chat there, okay? Is it an emergency?
I'll come by office.
Okay, I'll see you then. Take care, guys.